Very, very simple. Polynomial is just functions with multiple terms. So if you had two terms, right, a function that has two terms, we call that binomial, right? Bi means two, poly means multiple, right? So they all fit into the same definition. I say that not because this terminology is anything useful or profound. I say that just so that you know what you're being asked. Half of the battle for a lot of students when they do math is that they don't understand what the question is asking. How many of you can relate to that? Right. So it's, I bet a lot of you, it's like 70 or 80% of the math concept and can solve that problem, but you get stuck in the beginning not knowing what the question is asking you. So I'm trying to break it down simply. All these mathematical terminology can be broken down into very simple ideas. Polynomial, every time you hear polynomial, you're just like, yeah, I understand that. It's just stuff with multiple terms. Okay, that's it. Binomial, bi is two, so that means is functions with two terms. That's it, okay? Now, depending on the number of terms, and depending on the terms, the power of the term, when I say power, it means exponent, like x squared is 2 powers, right? X cubed is 3 powers, right? Third degree power, right? X4, 4 power, and so on. So the number of power, the degrees of power will change the shape of the graph of the function. Okay, so as an example, just idea-wise, so for example, if you have something like, look like this. This is a function called f of x. And this is a polynomial because in order to look like this, it has to have multiple terms with terms of different power in order to look like this. And we'll see how what makes what, okay? Certain parts of the function will make the graph look certain ways. We want to just be able to identify a few key ideas. Over here, there's a peak, right? There's rise and fall of the peak. This peak, we call this a relative maximum point. Relative maximum point. Sometimes some textbook will say local maximum point. Local, relative means comparison, right? Because this is not the absolute max. Why not? Because the graph can go higher eventually and surpass the height of this peak, right? So this peak is just relatively the maximum point relative to some, things around, but it's not the absolute height, the highest point. Same thing here, right? This one is just another relative max. Relative max. So I'm going to just use shorthand, RELMAX, right? Relative maximum point. We can also say local maximum. Now, what do you then think this point is? Yeah. That's right, relative minimum. Relative minimum, or local minimum. Right, local minimum. And same thing over here, we have another relative minimum. Does this graph have an absolute maximum? No. Does it have absolute minimum? No, because the function will continue to infinity going up as x gets higher and higher on the positive side, and the y value is going to continue to go into the negative infinity down that way as x goes in the negative direction on that way. Does that make sense? Yeah. Right. Now, so in a case when you have, say, for example, another graph, say it goes like this. Tell me what it has. It has an absolute max where? Yeah. This peak, right? Yeah, so this one will have an absolute maximum point, right? So that is the only difference. And then here, then we will also find a relative max. We have a relative min, and then that's it, right? And then this graph will continue to go to the negative infinity in terms of y direction all the way down, in either direction, x positive direction or x to negative direction. Now, there is a concept that there is a point, there's this point that is a concept that usually won't get introduced until calculus, but I'm going to share with you just so that you can ahead of time register. There is a term called a concavity. Concavity. A graph will have a curvature that is wrapping toward the upper direction. We call this concave upward. If you have something like this, we call this concave downward, concave down. So this is called a concavity. It's the arch, the curvature of the graph. Now, in algebra, we won't be able to study too much about the concavity, simply because we don't have tools to identify concavities. But later on in calculus, we will have tools to identify rather quickly what a concavity is, because, and you say, well, what's the point of that? Once you can come up with concavity, it can easily help you to sketch out graphs without any calculator tools, okay? Now, notice in this particular one, we have a concavity this way, right? This is the concave down concavity. Over here we have concave up concavity, and over here we have concave down concavity. We're over here concave up concavities. Between the up and down concavity, at some point, will they come to a head? Say, for example, you have a concave down concavity. When does this end, and when does this start? Somewhere in between, right? Yeah. Yeah, it could be somewhere here. This sketch obviously is not obvious, but one could assume that it's somewhere around here, right? This will at some point ending the curvature this way, and then begin to transition into curvature this way. Make sense? And we can assume that it is at some point, probably somewhere in the middle, This point when the curvature ends, one curvature ends and another curvature starts, this is what we call the point of inflection. Point of inflection. You often hear people use a inflection point talking about people's voice, right? When someone, a singer is singing, there's an inflection, or speaker, orator, you will say, oh, this person, the way they speak, there's an inflection point in their voice. Inflection point is this up and down, the changes of the direction. Does that make sense? So mathematicians borrow the similar words to describe these ideas. Okay, right now what I want to show you is I'm going to direct your attention to the screen. I'm going to see if I can actually do this. Here I have a TI-84 calculator. If you have it, you want to pull it out and follow along. If you don't have it, you can kind of look at what I do here and just kind of follow along if you like. TI-84. You've had TI-83, TI-82, I think they work pretty well. In this class, when we use calculator to help us understand things, we don't just use calculator to help us calculate. We use calculator to help us visualize ideas. And so I use calculator a lot, but use probably different than some of the reasons that some of you would use for. So what I do is I start out, you can look at on this side, this basically mimic your calculator interface. There is a button called, or typically you will have, let me see. Typically you will have something like this, right? Your calculator screen looks like this, right? Typically, when you turn it on. Now, right now, I want to look at some graphs. So I will go to this button right here called y = 2. I press this button, it will lead me to the screen. Now, I want to start out with some basic analysis. I want to do x. Oh, no. I want to do x. So I'll go here. This button has all these different variables. So you click on it, it's x. That's y1. Now, this calculator allows you to graph multiple graphs all in one space. So I'll go to y2, and y2 is gonna, I'll press enter. I'll go to y2. This will give me a red graph. I'm gonna press x again, but this case I'm gonna use x squared. So I go to the x squared button, and that's gonna give me that, and I press enter. Then I'll have x squared. Now y3, I'm gonna do x cubed. So I go back there again, x cubed, but instead, I want to go to power, so I press this button right here, right? This button right here, right above the division sign. I press this, and I press 3, and I enter. That gives me x cubed. And I'll do the same thing. I'll do x4, x to the 4 power. X to the 4 power, and then x to the 5th power. Enter. I have, and that's just for the fun of it. Do another one, x to the 6th power. X to the 6th power. Okay. Now, when I graph, I'm limited to a little tiny screen. But that tiny screen, I can zoom in and zoom out by changing the width of the x-axis and the y-axis, right? So what I do is I basically go to a window, right? I want to make sure I adjust for the window. I press this, I go to window. It says, well, in this little window here, you want x value and the minimum where? Yeah, maybe, I don't know, maybe. What do you think? Maybe a negative 10 would be, I think, a little too large. Maybe make it negative 4. How's that? All right, and then enter. Oh, go back again. 2. I'm having a hard time using the computer instead of pressing a button. How do I get to the next one? Oh, that's right, arrow. Yeah. No, that's not right. That's not right. How do I do that? How do I going back and forth? Yeah. Oh, yeah. I should use negative instead of minus. Negative 4. That's right. Thank you very much. And then I go arrow down. And I do 4, thanks. I know how to work on here. It's a little confusing over here. Maximum to 4. Now the scale is every 1 unit increment. You can do every 0.5, you can 0.1, doesn't really matter. Y value, I want to make it a little bigger. I'll make it negative 20. Oh, shoot. This is the problem when I'm, okay. Negative 20, arrow down, positive 20. Okay, so I set up the window. Now I'm ready to graph. So let's click the graph. What's happening here? That's okay. We can trace. Right, there is a button called trace. Where is it? Oh, right here. This one. Trace. Now I want to arrow this over a little bit further, right? I want to go over here so I can know what function I'm looking at. Now take a look at this. My cursor is blinking right here, and it's on the blue, and the screen shows I'm on y1 equal to x. y1 equal to x is a straight line, obviously, we know that. Now we can let it jump. I press arrow up. Actually, let me press arrow down. I jump to x squared. X squared is this red one. It's a parabola. Makes sense. We know this quadratic equation, quadratic formula, quadratic functions is a parabola function. Let's arrow again. This is x to the third power. X to the third power gives you this graph. Looks like this. And then I'm going to arrow down, arrow it again, and I go to the x to the fourth power. X to the fourth power is this pink graph that looks similar to the parabola, but just, right? It's not as wide, but it's much narrower. And then I go to x to the fifth power. Now, x to the fifth power is this green graph right here. And then x to the sixth power is this orange graph. Now, on your notes right now, I'm going to come around and see what you come up with. Give me a few takeaways by looking at these 6 different graphs. What are the patterns that you're seeing, or the lack of patterns that you're seeing? How are they contrasting from one another? What makes them, what you suspect that will make them look this way? To come up with a bullet point of a few ideas. Go ahead. Good. So we identify 2 things, or 3 things. Well, first thing is a line. Okay, a line. There's something to that line, right, by manipulating the x. So y is equal to x is a straight line. Straight line. Which is a point. I point this way. Right? So y equal to x is this line. And then y squared becomes what? Right, that square bends this line into this. And then when you get to x cubed, then what did it do? It tries to bend it back, right? But it didn't quite bend it back. You know how you take a wire, a straight line wire, and then you bend it, and you try to bend it back? Is it easy to bend it back and straight? Pretty hard, right? Is it going to kind of be a little crooked, right? So this is a line like here. You bend it into a parabola, and then x cubed, you try to bend it back, but it doesn't work out. It becomes this way. Becomes this way. Right? And then x to the 4th power, you bend it back again and go back here. And then x to the 5th power, you try to bend it back again. Like this. And then x to the 6th power, what happened? Like this. Yeah? It all starts with the line. When y is equal to x, or f of x equal to x, you can do all sorts of things to it by adding terms, by putting exponents, and you can bend this thing into different curves. But you notice some are this way, and some are at least this ways. What are the ones that will have this shape? Even number of the exponents, right? Make sense? When you have, right, f of x, this one doesn't have ink. When you have f of x equal to x squared, you got something like this. You have f of x equal to x to the 4, you got something like this. F of x equal to x to the 6th power, you got something like this. Right? So these are the even power. When you have f of x is equal to x to the q, you got something like this. F of x, x to the 5th power. You got something like this. Did we do more? We didn't do more, did we? If we do x to the 7th power, what do you think it's going to become? Similar, except it's going to be even steeper, right? So these are the odd number of powers. Now notice, as the power goes higher up, the fastest it gets to that shape. Because why? Because every value that you apply for x, it's gonna get multiplied itself by a lot more of itself, right? When you think about this, if x is equal to 0, then y is equal to 0. When x is equal to 1, this is 1 squared. If x is equal to 2, that's 2 squared, that becomes 2, 4. But over here, it's going to be 2 what? 16, right? And over here, it's going to be 2 to the 6th power, right? So it's going to go much faster. It grows much faster. And in this case, also grows much faster on one side, but decline much faster on the other side. You get it? That's the feature right there. Any questions? Now let me stop sharing for a sec. I'm going to move to this board. How are we doing? Are you still with me? You still with me? Okay. So let's take a look at this. F of x is equal to c0 x to the n power plus c1 x to the n minus 1 plus c2 x n minus 2 plus dot 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 plus however turn it takes to the nth term x n minus n. Okay? C0, I mean, this 0 is not really, I mean, it's 0, it's basically it's always called the initial term, right, to the n power, and then this power gets smaller and smaller. So this is what we call the lead term, right? This is the lead term with the highest power. And the power gets reduced, right? So if you have, say, you know, f of x equal to like 2x to the 4 power, then the next term you're hoping to have x to the 3rd power, x to the 2 power, x to the 1 power, x to the 0 power. What's x to the 0 power? Just 1, right? Anything to the 0 power is 1, right? Right? Yeah. X to the 0 power is 1, right? Yeah. We're good. Okay. 5 to the 0 power is 1, 10 to the 0 power is 1, x to the 0 power is 1, y to the 0 power is 1. Whatever to the 0 power is always 1. So guess what? This is just 1. 1 times that constant, this is what we call the coefficient, right? Coefficient this coefficient is a constant, is a value. So whatever that value is, that just becomes a constant. So if you have f of x is equal to x plus 1, then Cn is 1, right? If you have f of x is equal to 5x squared plus 2x minus 10, then your Cn is 10, right? Make sense? Okay, now what can we say about this? Obviously, we just understand that the Lie term has a power. You can determine whether it is even or odd, because that is going to give you a clue as to what your graph is going to look like. Okay? Now, what do you think this term will tell you? This is the last term that is a constant. So imagine you have some pretty complicated equation, and then what does this tell you? How can this term still survive when everything else gets killed off? I can put 0 in x, can I? If I put 0 in x, this term goes away, this term goes away, this term goes away. If you have so many 100 terms over here, the 100 terms is going to go away, except this one, because 0 to the 0 power in this case is still 1. 1 times whatever that non-answer is still whatever that answer. So when x is equal to 0, the function ends up to be this value. This value turns out to be what? When x is equal to 0, we're talking about that this function is passing the y-axis. Right? Think about it this way. Take, for example, f of x is equal to x squared minus 4,000x plus 2. Okay? I can go crazy. I can, whatever. And then you put f of 0 into here, you get 0 squared minus 4,000 times 0 plus 2, you end up with 2. Right? Where does 2 come from? It comes from here. And when you graph this, this is a coordinate of x equal to 0, y equal to 2. 0, 2, 1, 2. So when all else fails, I know that this function, if I know nothing about this function, I know at least one thing. This function is going to pass through the y-axis at 0, 2. So what does this term tell you? The y-intercept. Right? That's the y-intercept, isn't it? Yes. Right? And this function is going to look like this. Right? It's going to pass through this. So it doesn't really matter what this is. It can be all sorts of different shapes like this. But we will know one thing. The last term with a constant term. Now, if you don't have any constant term, that means that's 0. So your y-intercept is at 0. If this number is some other constant outside of 0, you know exactly where your function is going to cross the y-axis. Y-intercept. Questions on this? Yeah. So you notice. Over here, when we were looking at these graphs over here, I'll bring my computer here just so that it's in part of the discussion. If you look at this, right, you got x squared, x4, x6, x3, x5, x7. You only got one term, and I do this simply because I only give you a function of one term to analyze what the highest power is going to do to the graph. Obviously, these graphs are going to change just slightly a little bit if you begin to add extra terms, right? Something like this is going to have multiple terms in order to bend that graph in these ways. Okay? And we will get to that. Okay, we don't have to worry about it for now, but we will get to that. Let me erase this part and then we'll go over a few examples. Now back to the algebra of it. What I just did with you is just for you to look at the function and these terms would do to the functions. But this is a very simple problem, just to get started. Adding and subtracting polynomial, right? Add, subtract, polynomial. Example, a very simple example. You got 6x cubed plus 4x minus x squared minus 7 is a polynomial. It's not a function, it's just an expression. You subtract a second polynomial, another big term, right? Big thing. 2x cubed minus 8x squared plus 3. This is very, very easy in terms of adding or subtracting polynomial. You simply combine like terms. When you combine like terms, you have to make sure that the variables are the same and they have the same degrees of power. So x squared and x cubed are not like terms, but x squared and negative 3x squared are like terms. You see the difference? So in this case, we're going to combine the like terms, but notice we have parentheses and we have a minus in front of the parentheses, so we must adjust accordingly. X cubed by 6x cubed plus 4x minus x squared minus 7. Minus still out here, but this minus applied to every single term as we go inside, right? So then the first one is negative 2x cubed, right? Negative 2x cubed minus 2x cubed. This is negative 8x squared, but minus out here becomes x positive 8x squared. This is positive 3, this is negative out here, so it becomes minus 3. So now you just need to combine like terms. We have first set of like terms, the x cubed, like 6x cubed minus 2x cubed. 6x cubed minus 2x cubed give you 4x cubed. You just have to be able to take inventory of this. Make sure you keep track. The next one has to be 1 power less than x cubed, right? X cubed is the highest power, so you want to look at x squared. So we have x squared right here, right? X squared term. These two terms are x squared terms. Negative x squared plus 8x squared is positive 7x squared. Positive. That's why I put plus sign in front of it. Okay? The next one, after we have done the x squared term, we do the x to the 1 power term. So this is the x to the 1 power term. There's only one of them, right? This is only one of them. I don't see anything else. So in this case, I will add for x right here. Lastly, I have minus 7 and minus 3. That's also a like terms because they're constant. They are the ones with x to the 0 power. So I have negative 7 minus 3. I got negative 10. Voila. Box this. This is your answer. Questions on this? I feel like it's too easy for me to even, but I had to go through it just to make sure that you know what to expect. Next one, multiplying. Multiply polynomial. Okay, so you have 2 plus 5 times x plus 4 times x minus 3. Something like this. Multiply. Well, this is just multiple FOIL, right? Multiple, like you multiply them out. I'm sorry, this is not 2. This is 2x. I wrote it wrong. 2x plus 5. Now, you can go ahead and just multiply out these two binomials, figure that out, then multiply by the last one. Straightforward, very simple. I look at it, I want to be a little easier for me even, is that I look at this as 2x, so I thought, okay, this one only has x, and this one only has x. I'm going to go ahead and multiply these two terms first, before I multiply this out. So I'll keep the first one out. It doesn't really matter which way you do it. Right, so 2x plus 5. Now, x plus 4 times x minus 3, so let's multiply this out. Put a parenthesis around it so you can keep track. This is x squared, right? Minus 3x plus 4x minus 12. So far, so good? This is, again, 2x plus 5. Keeping out here, simplify this a little bit. This is x squared plus x minus 12. Move it out here a little bit. Now, so right now, I just go ahead and multiply this out, right? So 2x times x squared, I get 2x cubed. 2x times x, I get positive 2x squared. 2x times negative 12, I get negative 24x. 5 times x squared plus 5x squared. 5 times x is positive 5x. And 5 times 12 is 6b. Yeah. Yeah, I know. That's why I'm rushing. Okay, combine my terms. I got 2x cubed. That's only one left. We got 2x squared, 5x squared. We got 7x squared. I have minus 24x and plus 5x. What do I have?
Minus 19x.
Minus 19x. And then plus 60. Okay. The next one I want to show you, before we leave, I'm going to take off 2 minutes of your time. Now, it seems like these ideas are they're not necessarily connected to each other, but next week I'm going to put it all together and they will all feel like they're all connected to each other. Okay? Here you go. Factoring polynomial.
No.
In order to factor them, we have to use some identity. What's identities? It's not personal identity or anything other. This is just, in math, this means proven patterns. Proven patterns. Okay? Proven patterns. Okay? So first proven pattern is this one. A plus B squared. Now A plus B squared is A plus B times A plus B. You factor this out, you get A squared plus 2AB plus B squared. A minus B squared is equal to A minus B times A minus B. If you take the time to get through like what we did over here, multiplying it out, you're going to have A squared minus 2AB plus B squared. The only difference is a plus here, minus here. Okay? This is the first one. So for example, how do you use this idea to factor? multiply out 2x squared plus y cubed squared. Now, you can do the same thing by doing, separating into two. But what we can do to leverage this idea is to say that I can think of this as a as 2x squared and b as y cubed. If I do that, right, I notice this is a plus b parentheses squared, which follows this. So then I can say, okay, a squared, I can follow this identity. I can say a squared is 2x squared squared, right? Because a is 2x squared. So a squared is this whole thing squared. Plus 2a is 2x squared. And b is y cubed. Plus b squared, which is y cubed squared. And when you do so, right, 2x squared squared, 2 needs to be squared, so it's 4. X squared squared is x to the 4th power, plus, right, this is just 4, x squared, y to the 3rd power, plus y to the 6th power. So you can see the usefulness of using identity. I haven't even shown you the factoring, because the factoring gets even useful when we're dealing with something like this. Let me quickly write down another one for you. Another one is when you have a minus b times a plus b, you end up with an a squared minus b squared. This is extremely useful because notice this. This is something squared minus something else squared. We call this the difference of squares. What that means is that if I come up with an expression that look like this, I can quickly factor them into this. It's extremely useful, and I'll show you how to do that on Monday or Tuesday, the next time I see you.